Welcome to the second lecture, Programmable Logic Controllers, PLCs, an overview. Today's topics are as follows. We will define what a programmable logic controller is, list the advantages of PLC over relay systems, identify the main parts of a PLC and describe their functions, outline the basic sequence of operations for a PLC, and finally, we will identify the general classification of PLCs. Programmable logic controllers are now the most widely used industrial process control technology. A PLC is basically a digital computer designed for use in machine control. It has been designed to operate in the industrial environment and is equipped with special input-output interfaces and the control programming language. So as you could see in the picture, we have one example of a PLC. Initially, the PLC was used to replace relay logic, but its ever-increasing range of functions includes timing, counting, calculating, comparing, and the process of analog signals. The structure of a PLC is based on the same principles as those employed in computer architecture. So here we have one PLC and here we have one laptop, and you could see that both of them are quite the same. They have CPUs, but they have different applications. They are designed for different environments. Programmable logic controllers advantages. So here we could see a relay control panel. So these are relays, each of them are one relay. And you could see a bunch of wires needed to connect those relays together. And here we have another panel based on a PLC control. So here you could see a PLC control. We have much less wiring. Elimination of much of the hard wiring associated with conventional relay control circuits are one of the most advantages of PLCs over relays. So traditionally, before having PLCs, it was common to use relays to have a control system or industrial control system. Programmable logic controller advantages. We will continue with other advantages of PLCs. One of them is increased reliability. Since all the logic is contained in the PLC's memory, there is no change of making a logic wiring error. So if you want to have industrial control system based on relays, we have to change the wiring to have a different logic. But in PLCs, we just need to change a program. So here you could see we have one example or one user program here, which is coded in the memory of the PLC. And if we want to change the logic, we just need to change the program of the PLC. Another advantages of PLCs are basically flexibility of PLCs over relays. So we are continuing making comparison between PLCs and relays. So it's easier to create and change a program in a PLC than to wire and rewire a circuit. So we don't basically touch the hard wiring in a PLC. The inputs and outputs, these are inputs and these are outputs, are, let's say, the same, and all of them are connected to the inputs and outputs ports of the PLC, and if we need to change the logic, we just need to change the program. Another advantage of PLCs over relays are lower cost. Generally, if an application has more than about a half dozen control relays or 6 relays, it will probably be less expensive to install a PLC. Okay, so if we have in one application more than 6 relays, it's just cheaper to have a PLC replaced by all those relays. Still, relays are common in industrial applications, but they are good when we have usually less than 6 relays. Another advantage is communication capability. A PLC can communicate with other controllers or computer equipment to perform such functions as supervisory control, data gathering, monitoring devices, and process parameters, and download and upload the programs. So we cannot achieve these functionalities with relays. We cannot gather data. We cannot monitor devices with relays. But with PLCs, we will be capable of doing such performances. Another advantage will be faster response time. Machines that process thousands of items per second and objects that spend only a fraction of a second in front of a sensor require a PLC's quick response capability. So look here, we have a conveyor and we have these buttons on the conveyor. So based on the sensor response and the speed of the conveyor, we need a appropriate processor to process the data coming out of the sensor. Otherwise, we cannot, let's say, count these bottles and we lose some information. Another advantage of PLCs over relays is easier to troubleshoot. To find and fix problems, users can display the control program on a monitor and watch it in real time as it executes. So you see that the PLC is connected to monitor, and we could monitor and watch in real time how the program executes here. Okay, in what stage we are, and we could then easily troubleshoot or change and modify or enhance our program. Okay, the next section of this presentation is about parts of a PLC. We want to introduce you what are different parts of a PLC. The major parts of a PLC system are the central processing unit or CPU, the input-output or I/O section, the power supply, and the programming device. So here in the picture, you could see a CPU or a central processing unit, the memory section, we have the input module, which we could connect our input devices. We have output module, which we could connect output devices to the output module, and we have programming device, or let's say PC or laptop, which could be connected to PLC to monitor the program, to download the program, to upload the program from PLC. So these are the main units of a PLC. And of course, a power supply, yes? So we need a power supply to supply power to CPU, to input module, and to output module. Okay, now we want to see what could be possible architecture of a PLC. The term architecture can refer to PLC hardware or to PLC software or to combination of both. So that architecture could be used for both software and hardware. Now we have two kinds of architecture: open architecture and closed architecture. An open architecture design allows the system to be connected easily to devices and programs made by other manufacturers. Okay, so what does it mean? It means that we don't need to have a special program for that specific PLC. You could use some other generic type of programs to upload and download PLC programs to that hardware. A system with a closed architecture is one whose design is proprietary, making it more difficult to connect to other devices. Okay, so we need to have basically a specific piece of components coming out of one specific render company, and we could only connect those components together. For example, Siemens PLCs they have closed architecture, and we could only use a Siemens PLC with TIA portal, which is designed and programmed for these specific hardwares. On the other hand, we have, for example, Codesys, and Codesys is has an open architecture and could be connected to a variety of different hardwares, if that is allowed by that company. We could have two kinds of PLCs, one with the fixed I/O and one with the modular I/O. Fixed I/O is typical of small PLCs that come in one package with one separate removable units. The process and I/O are packaged together. So here you could see variety of fixed I/O CPUs. And here you could see that the CPU and input sections and output sections are all packed into one box. Here you could see one example of how we could connect these type of fixed I/O CPUs to input and output modules. Modular I/O is divided by compartments into which separate modules can be plugged. This feature greatly increases your options and the unit's flexibility. So here we could see one type of these modular I/O CPUs. Here is the CPU, and here we could see input and output modules. Here you see that we have, let's say, a power supply, a processing module, or CPU, and then we have input output modules here. So we could connect different type of input output modules on this rack. Okay. The power supply provides DC power to all modules that plugs into the rack. For large PLC systems, this power supply doesn't normally supply power to the field devices. Okay, so here we have the power supply, and here we have CPU, and then we have input output modules that we could add those input output modules on the rack. The processor or CPU consists of a microprocessor for implementing the logic and controlling the communications among the modules. The processor requires memory for storing the results of the logical operations performed by the microprocessor, as well as the operating system and the PLC program. The PLC program is executed as part of a repetitive process referred to as a scan. So we have a repetitive process and we call that repetitive process scan. That process starts with the PLC reading the status of all input. So here, this is the start. We read inputs. We have sensors, we have push buttons. So we need to collect the input. Then, based on the input, we'll move on to the program to execute program. And based on the logic of the program, then we will have updated outputs. But before that, we could have this stage of diagnostics and communication. We might send information to other PLCs. And then finally, we have update outputs. We send output to the output field devices. So it concludes with the updating of all outputs. It's very important to understand this scan process in our troubleshooting and writing PLC program. The I/O system forms the interface by which field devices are connected to the controller. So here we have input module, and here we have our field devices, let's say sensor, push buttons, limit switches, etc. All of them are connected to the input module of the PLC. Input devices such as push button, like this one is a push button, limit switches, and sensors are hardwired to the input module terminal. Once we connect these input devices to input module of PLC, then we don't need to touch the wire anymore later. Okay, here we have the output module, and again we connect output devices such as motor, starters, solenoid valves, and indicator lights by wires to the output module terminals. So here, for example, we have motor, we have pilot lights, and we have solenoid. All of these devices are connected to the output module. So here you could see, for example, the field device power supply could be different from the input device power supply. In this example, we have 240 volt AC, but the input could be 24 volt DC. A programming device is used to enter the desired program into the memory of the processor. We could have two types of programming device. One is called handheld programming device. Okay, so these are portable programming devices. And the other one, the program is entered using the relay ladder logic programming language, in this case buy a PC or laptop. Of course, in PCs or laptop, we have more flexibility of monitoring the program and changing the program. But in handheld devices, we don't have such flexibility. But since it's more portable, it could be used for, let's say, applying small changes and quick changes to the PLC. Personal computer PC is the most commonly used programming device. The computer monitor is able to display more logic on the screen, thus simplifying interpretation of the program. So here we have the monitor. You could see the uh, the ladder logic program here. Um, a program is series of instructions that directs the PLC to execute actions. Relay ladder logic, the standard programming language, is based on electromagnetic relay control. So the ladder logic program is the most commonly used program in PLCs, and it follows the same logic as connecting relays by wires. Yes, so instead of wiring and rewiring real relays, we just connect and disconnect those relays inside the program. So these are instructions. Okay, these are branches, and we call this one a rung. Okay, so rung. So we have two rung here. On this rung, we have two branches. Here we have different type of instructions. Okay,